All right. Hello, everybody. Hopefully you can hear me and the audio is working well. Welcome to our inaugural episode of PyTorch Community Voices. Today I'm Randall Hunt. I'm a developer advocate here at Facebook, focused on PyTorch. And I'm joined today by Suraj and Jessica, and I'll let them introduce themselves.
Hey everyone, my name is Suraj. I am a developer advocate at Facebook AI, and I work closely with PyTorch.
Everyone, I'm also a developer advocate, and I'm focusing on a lot of our AI ML products in our open source AI ML products.
And you can see that Suraj and Jessica are significantly more prepared than me because they have the fancy green screen going on. And I'm very excited to introduce our guest today, Thomas Viehmann, who is a very prominent member of the PyTorch community. And Thomas, I'd love for you to go and introduce yourself.
Hi, yeah, thanks for having me on the webcast today. So I'm Thomas. I've been contributing to PyTorch for 4 years this month, actually. It's been 4 years that I sent my first PR. And so I tried to do various things. I think I helped someone on the forum the other day.
The other day? Every day?
No, not every day. But, I'm trying to be helpful every now and then. And then I also wrote with Eli Stevens and Luca Antiga. I wrote the book Deep Learning with PyTorch, which you could download for a while from the PyTorch website. And then our latest, and this is also with Luca Antiga, is that we created TorchDrift, helper library that helps you keep an eye on your model when you think you're done with it. And so this is what we're going to chat a bit about today too.
Awesome. And I understand you have a interesting presentation prepared for us on TorchDrift today.
Well, I hope.
All right, so we've got about 30 people watching right now, so I wanted to go ahead and say to all of you, the way that this is going to work is Thomas is going to give a 15, 20-minute long presentation walking through TorchDrift, which is the library that he and his colleagues have authored, although I only see you in the Git commits. So then we'll be taking questions from the audience. So feel free to type your questions in as we're going through the presentation. And then if you have any specific questions and we don't pick up on them, you're welcome to just tag one of us in the chat, either on Twitch or on YouTube. And with that said, I'm going to take myself, Suraj, and Jessica off of the screen. We're going to put up Thomas's presentation, and we're going to get going. And thank all of you for joining us for this inaugural episode. We're really excited. Please let us know whatever feedback you have. Okie dokie. Thomas, are you ready?
Yeah.
All righty. Take it away.
Okay, so first thing I should say, so this is from Methanth, which is my company, but it's joint work with Luca Antiga and a number of other great people from Aerobics. And also Luca did the logo. So TorchDrift. When you have a model and you want to do something real with them, you need to be sure that it works. So you have a really, really strong requirement that your model works. And so Aerobics, and Luca always is too modest to mention it, but I can mention it. They have a platform to facilitate deployment and governance and the lifecycle management for models. That's called Invariant AI. And so they have these industrial clients who do, for example, quality control using vision algorithms. And so now it's absolutely critical that the models work as expected and detect any defects in the same way as they were trained to do. So at all times, I need to know if my model still works as expected. And so how do we do this? Well, we have to keep a lid on drift. And now you might wonder, what is drift? And if you Google the term, you have all these various things. You have input drift, labor drift, concept drift. And then there's things that happen slowly and gradually, or you have a regime change, which is kind of the fancy speak for something suddenly happens. And all these things kind of work around the key question, which is, do the assurances that I get from model validation still apply when I deploy the model, when I run the model? Do they degrade over time? Or can I say, well, yeah, I validated my model and the test accuracy was 99%, and I expect that to be the same accuracy that it gets now that I have it in production. And so there is this path. So the first thing is you need to absolutely validate and test your model, and you need to do it with production data, right? Nothing is more embarrassing when you have a validation set and in the end the model doesn't work because the validation set, even though you thought it would, because the validation set somehow didn't represent what the model sees when it's deployed. But if you have done that, you have to be sure that you're still in the same setting. And so you can ask yourself, well, can you check the model by kind of revalidating? But for this, you would need labeled data to kind of compute the accuracy against the ground truth. And you would have to have this somewhat cheaply, because we all deploy these models because in vision models, the computer can look at more things than people can look at. Or you might have the luck that you have somehow managed to train a model that can say, I don't know, when it can't make sense of its inputs. For example, Bayesian techniques kind of show some promise here. But so if you have any of this, you are essentially extremely lucky. And the largest proportion of models doesn't have that. They're overconfident, and in production we don't have labeled data because it's just the inputs are just buzzing by. And so in this situation, you're likely okay as long as your production inputs are very close to your validation inputs, because then if you have the same type of inputs, you can believe that your validation results still apply. And so TorchDrift is here to help you check exactly this. Is the things that my model is doing still the same thing that it did during validation? And so to look at this and to talk a bit more about TorchDrift, we should get a bit more technical. And so let's imagine that all my images are embedded in a two-dimensional space, and I plotted it here. And you have the blue dots on the right that are the inputs or the intermediates or the features that you saw during validation or during calibration of the drift detection. And the orange dots, they're just in the same situation. They're statistically indistinguishable because they actually came from the same distribution. And then you don't have drift. And now, if you have drift, for example, if you look at the green dots here and the green circle, you see that it's not in the same place. And so the inputs, or the features, but typically it starts with the inputs, they have shifted. and I give a reference here, a paper, Failing Loudly, which is a good overview of drift detection. But so this sounds good. It's a known thing, and it's kind of easy to work with the statistical testing. But now comes the difficult part. So the first thing is which features to use, right? I need two-dimensional features if I want to plot it like this. But more seriously, you do have a curse of dimensionality if you go to very high dimensions. So just throwing the image into whatever you want as the result is likely not to work as well as something more sophisticated. And this is really the same thing as classification, if you want, in image processing. The other danger is that you run into something which is model blindness. So you could say, well, yeah, I'm just going to use the features of my model or even the output probabilities after the softmax at the very end, the outputs. But there you might run into the problem that, well, yeah, your model has ignored so many things, and maybe it also ignored stuff that is actually relevant to you. And so we have to be a bit careful about this too. And then there's all the governance parts. And so the next thing is when to sound the alarm. And so I told you, and you might believe it, that the green sample is statistically detectable different from the reference distribution, the blue dots and the blue or purplish circle. But so this might be completely harmless because it's still so close to our reference distribution that we don't care about. And we might only care if things shift like fully out of the region where the model was trained, like if it's now the red distribution. And so the region in which the model does well might be different from what statistical testing identifies, or where statistical testing says that it cannot detect drift. And so we have to find a way to calibrate when to sound the alarm, which is, of course, in the end, very similar to any type of exercise where you have to have a binary classification and you want to have something like the receiver operating curve statistic and choose a point to balance the errors of false positives and false negatives. And of course, we have a very good discussion, and Eli was the lead author on that part, discussing this kind of trade-off. But so we have this trade-off here, and of course, we also have the task to somehow integrate it into production. It's kind of like if you watch how the milk cooks on the stove, you don't want to know when it started spilling, but you actually want to take it off the stove and do something with it. So the question is, how do you integrate this into your production chain? And so we started this, and we worked a lot on this. Randall said that, well, yeah, all the commits in TorchDrift are from me, which is true, but really the code is kind of part of the end product. But just like it's not only the person that wraps the present that produced the present, if you give a gift to someone, just because the git commits all have my name, it doesn't mean anything. So it's with Luca I mentioned, but also with Lisa Lotza and Daniele Cortinovis, from aerobics. And we first started this internally, and then look at some point said, well, yeah, could we also provide this to a broader community and open source it? And so we created TorchDrift, and we have quite a bit of documentation at torchdrift.org, and there's also the GitHub repository approximately where you would expect it. The general approach that TorchDrift takes, and I showed this a bit, is that we have some sort of dimensionality reduction, and then you do statistical hypothesis testing, and you have some test statistic, and based on this, you have to say, well, yeah, if it's here, then we're going to say, hey, here things have drifted. And we can play this in different flavors. And so one thing is we can take the input, like we can take the images, and we make our drift detector have a reducer that reduces it to some lower number of dimensions, anything from 2 to 1,000. And then you have a detection, which is typically a standard 2-sample test. And you get the drift score. Either you have this as an output or you do something with it. You can also take an intermediate layer when you kind of detect the latent drift. And the idea is that the lower levels of our models, typically, they do things like edge detection, right? A couple of years ago, there was all the rage that you put in all the lower level filters, or you print out you display all the lower level filters. And so you could say, well, yeah, this is an edge detector, and this detects corners on the second layer. And so the first few layers might be benign in the sense that they extract interesting bits, but they don't lose too much information that we might want to use in drift detection. And you can take the drift detector and hooked into this, or you could take the feature extractor from the model as a whole, or you could just use a standard feature extractor that you're trained on ImageNet or whatever. And then you feed this into the detector directly if it's already of low dimension, and then you get the drift score. These are kind of the main different flavors that I would see here. We built this into an API, and just like you would expect from something that tries to be PyTorchy, and obviously we try that a lot, these detectors and reducers are just NN modules. You have the kind of special aspect that in addition to the forward method, you have a fit method, because these things are set up not by training through gradient descent, but you have a fitting procedure that kind of takes the reference data as inputs and then it just stores them away or processes them in a way. But after you do the fitting, you really just call forward and you have inputs and you get out either a drift detection score, some sort of distance metric thing, or you can convert this into a p-value currently. And we also have coming up something that you converted into what we call a z-score, and that kind of has an intuitive, a more intuitive metric than having very, very, very low p-values. Our experience in terms of governance is if you say p-value, people say, yeah, 1% or something like this. And usually for this type of exercise, 1% false positives, which is what the p-value calibrates, is very, very many. And so these are NN modules, and you can compose them and stick them into sequentials and do all these things and you can trace them if you want to deploy it in a TorchScript context, and we're working on also enabling scripting. Okay, so how would deployment look at as a process? And again, this is very important. TorchDrift is a technical thing, and it's a library that you can download from GitHub. But really, there's a process aspect that's really important. And so the deployment works that you baseline it either as a preparatory step or directly from production. That you say, well, yeah, the first 2 days of our production are just the reference. And then after fitting, you have this NN module, and you can either run the drift detector completely separately on the input or on intermediates. You can run it from a hook. You can insert a hook into your main model that kind of does this branch that we saw this graphic with the 3 variants of playing it. Or you can integrate it into the deployed model, and then you have an additional output that you can process by the output's consumer. And obviously, there might be a combination of this too. For example, there might be a drift level when it detects a certain drift level, torch drift. You might say, well, yeah, this is something where we alert an engineer to look at the model and what it's doing. Or there might be something that's so large a deviation that you have to say either, well, yeah, stop the factory, or you might have something where you say, where you attach a warning to the results when they are presented to the user. Okay, so back to the gaskets. Here's what the colleagues at Aerobics did with the gaskets. They took an ensemble of autoencoders to reduce the dimensionality of the input, and so that they didn't use the trained model in order to not have kind of these blindness effects. And after this reduction step, they just applied one of the statistical tests that we have, and this was the minimum mean discrepancy, which is kind of the flagship test, if you want, which is kind of in our experience, the go-to test that you can use first until you have a reason not to use it. And the beauty of this is that you also can see kind of where this comes from, and this is the background function that is lighter on one side and darker, and when you have a red dot on a dark space or a green dot on a yellow space, then these contribute a lot to the detection of drift, to the statistic that causes the model to say, where here the statistical test for drift is points to significance. So this can then help with the analysis, and now you can ask yourself, can you tell the difference in what we did here? Okay, so brief look into the future. So our goal is to have a one-stop shop for drift detection here in the PyTorch ecosystem, and also to integrate better and continue to integrate better with TorchServe or Redis AI. We're in the process of adding new detection approaches too. And we're really excited about that. And I tried hard to see whether I can show something today, but it still takes a few more weeks, unfortunately. Okay, and then we want to enhance the TorchScript support, but also we want to further develop the best practices around this, because I think just the library, it's good to have, but it's you're not done when you clone the library, but there's something around best practices, both for the technical aspects, how do you actually get this to work well, and also for the governance. Maybe that would be a good chapter 18 in our book, if there's ever a second edition. We'll see. And so this is where, with this little outlook, I'd say we'll bring Randall back in. Thanks so far.
Thank you, Thomas. And I'm also going to bring back in Suraj and Jessica, and we'll have all of us up here, and we'll have a little conversation for a bit. Your last slide, the future of TorchDrift, actually addressed some of the questions that we had for you, but I want to go back a few slides and recap everything for the audience. So thanks again for everyone on Twitch and everyone on YouTube for joining us. Now is the time to start putting in your questions. So based on that presentation, based on really anything PyTorch related or anything you want to talk to Thomas about, you've got him for 15 more minutes. So please just let us know what you want to know. Type your questions in chat and we'll get them up on the screen and we'll see what we can do. So I have some questions in the meantime, and I want to go back to something that you were talking about earlier on in your presentation, which was about using this in production and how you can basically add in these hooks for detecting drift. Do you have any more detail on that? Is there anything interesting to know about that, and any examples? I guess the gasket example.
Well, so I think in terms of well, there's two parts to this, and you say the gasket example. And so the first part is kind of the mathematical part, and this is
mathematical.
Maybe, yeah. Well, I should have started with the other one. So the first part is the technical part, of course. And here we're being really kind to you because it's all kind of vanilla PyTorch models. You can just either you assign it into your model and then it's magically there. That's the usual PyTorch magic that does it all. Or you can use PyTorch hooks, and PyTorch hooks will also allow us to just seamlessly connect in there. And then you can apply it with any deployment solution that lets you run PyTorch models. And so that's really cool. And we actually have an example of how to do that on our website, TorchDrift.org, which I think it works with like ants and bees, and you have kind of a toy example of a model, but then you can see how you hook into the model with hooks, and it's just the usual PyTorch mechanisms. And maybe this is one of the strengths of TorchDrift, is that it tries to not get into your way, and you don't have to learn anything new about production. So the other part of this is the mathematics. And we saw there was a choice to be made at various parts, like when to sound the alarm and which features to use and which reducing mechanisms to use. And to be honest, while we have some feeling that some things work well and some things work not as well, we don't have it down to a cookbook recipe yet. So there's some experimentation in there. And sometimes things work very well, and sometimes you have to kind of tweak things to make them work. Yeah, and also this is statistics. And you've seen that I've tried hard to not say the drift detector says drift happened, but just says, yeah, the statistical testing says there's a significant and so on, right? And this is always in there. And you have to kind of keep in mind that we're kind of making funny things with the statistics. If you have like a p-value of 1% and you have like a million things that run through your model, you suddenly have 10,000 false alarms, right? And so these things are a bit hard, and they take a bit longer, and it's maybe not. It's 10:30 in the evening. You mentioned it earlier. For me, it's not something that you chat over beer.
Yeah, it's difficult.
But you can figure it out, and then TorchDrift tries to make it easy for you to run a few experiments.
And you can do, essentially you're running those experiments, adjusting those values and saying, hey, is this threshold what I want for my production? So maybe you can like do small little logs in the beginning.
Right.
All right, I want to take a question from the audience right now. So Fernando has asked, do you think it would make sense for some of the TorchDrift features to be added into the standard PyTorch library?
Yeah, I think it's kind of a difficult question, and so there's several parts to this. One part is that, of course, everyone wants to be part of this PyTorch standard library, but at the same time, I think that if we put it in there and then it gets outdated, it's kind of very hard. And for example, at the moment, there will be things that might change the API in an incompatible way. We're still at 0.2 in terms of versions. But I think this is kind of something that works well separately. But we're trying to feed things that we need into the main PyTorch library, for example. And now I'm giving away one of our plans. I currently have a PR open in PyTorch that waits for me to fix some GPU computation for log space matrix multiplication. And we need this for one of the new statistical tests we want to implement. And I think it's good to have the infrastructure there. But things like this, a pure Python library, that works really well outside PyTorch too, and it works really well in the ecosystem. There's one thing that you can actually learn, or one thing that is hard for people that provide third-party libraries. And if you get Edgar Riba on, the person or one of the lead developer of Konya, and we chat about this a lot. One thing that is extremely hard is this version matrix that PyTorch has for GPU kernels. That you have like CUDA 10, 11, 12, 13, or maybe they skipped 13 because it's bad luck. And then you have Python 3.6, 3.7, 3.8, 3.9, and now 3.10. And for a third-party library to support all these combinations, that's really tricky. But for pure Python libraries, I think it's good for them to mature a bit outside the ecosystem. And then at some point, you might say, would it be good to kind of move into the PyTorch organization?
Gotcha. That makes sense. Jessica, I think you have a question.
Yes, I did. So I wanted to go back again to your discussion about future work. So you mentioned a bit about a few different detectors that mostly from the Failing Loudly paper. So I wanted to dig a bit more into that and see, can you talk a bit more about any new detection methods that you guys are going to be adding in future developments?
Yeah, so actually we're looking at some of the things that aren't in the in the very, very controlled environment. And so, for example, if you have something that controls search queries, and now you have, for example, for Wikipedia, if they want to check how their search works, And now they have a hot button topic, and everybody on a given day, like today, Italy dropped the charges against Carola Rackete, who saved 50 people from drowning in the Mediterranean, and then she got prosecuted, and today they dropped the charges, and now everybody looks her up on Wikipedia to be kind of on top of things. And now this will not look like the average Wikipedia. There is no average Wikipedia search day, right? If you have these clusters and kind of how to work with them, this will be one of the mathematical things we're going to add. Probably the one that I'm most excited about.
That seems extremely useful, especially, I can see that being used, especially in places where you're doing, say, like log analysis or something, and you want to be able to serve relevant things to developers. There was a great kind of prediction recently. There was a great paper that came out recently. I don't remember if it was Netflix or somewhere else, but they talked about how they built a model for showing build failures, and they actually used drift detection in that to say like, hey, is this the relevant log line that we should display or not? And then we've got a couple minutes left, everybody, so get your questions in. And in the meantime, Suraj, I think you had a question?
Yeah. Thanks, Tom, for the presentation. At PyTorch Ecosystem Day, Mikhail Fair mentioned that they use TorchDrift in Disney's Creative Genome project, which is why I'm curious. When people are using different types of models, what signals and thresholds do you suggest or recommend that people should look into?
Excuse me, what?
When people are using different types of models and they want to detect drift across different types of models, do you have any pointers for what signals or what thresholds that they should be looking at to measure?
Suraj, I think you might have missed our previous conversation on this, but yeah, anything else you wanted to add there, Thomas?
Yes, so I think kind of once you have it in, like, you always want vector spaces or points in some vector space, right? And that's universal. You have the word vectors and you have the fancy vectors nowadays for this. You have the ImageNet features. Whenever you have a vector, you basically won. This is one of the things I like about our book, that we do a chapter on data representation at the very beginning. And if you read this, you know what to apply TorchDrift, the detector, on. And so I think that's one of the great things about machine learning, that you have this universal representation thing.
All right. And I know we're coming up right on the limit of our time here. We have 5 minutes left. So I'm going to go ahead and skip ahead a few questions and say, Thomas, you're actually a pretty well-known figure in the PyTorch community. And I guess a question that I have for you is, how did you originally get involved with PyTorch? What is it that caused you to spend this time on the forums and help so many people out and help grow the community the way you did?
Yeah, I was just looking to do more of the machine learning things after being an actuary for 10 years. So I did a lot of insurance modeling and stuff like that. And I have this background a very long time ago, like 2003 or something like this. I used to be a Debian developer. And so I was kind of, perhaps not consciously, but I was looking for some sort of community to be part of. And with PyTorch, this kind of worked out really, really well. And one part was the forums and the great people on the forums. And obviously, I'm a huge fan of Piotr Bielecki, who is kind of the face of PyTorch on the forums, and one of the most generous people I know in general. And then there was a GTC at Munich, actually, and so I chatted up after having the first PR, or maybe the first 10, I chatted up Sumit and say, Willie, I want to have a beer. And so I got to meet some of the people in person. And this kind of got me started. And then I started a meetup here. And so it was all gradually. I always joke that I just do this for people, really. And kind of this is what drives me in a way. That's
pretty amazing. I can't wait to visit Germany and talk with you. All right.
Yeah.
So I think we're gonna go ahead and close out. We have 2 last questions for you here, and they're not specific to your presentation today. So Jessica, I think you had a question, right?
Yes, I did. So this is not at all, doesn't have to be related to this presentation or to PyTorch, but what are you excited about just in general? Maybe, well, it could be in the AI space overall.
Yeah, like what are you most looking forward to in machine learning? So what's the thing that's next on the horizon for you that you're most excited about?
Well, so I'm going to say what I'm most excited about today. And so I think, and I'm living for the moment here. But so I think that the machine learning thing really gives us a whole new paradigm how to tell computers what to do, to shift like from programming to training. And we're coming to a point where you can achieve great things just by using the existing models and having your data set and your opinion about what the outcome should be. And you can teach computers by showing them, this is what the outcome should be for this input. And this is dramatically different from how we used to like program computers, right? I got my first computer in 1984, and I had to tell them how to make a bar graph by doing funny things. And so this is kind of the thing that I'm excited about, that people that have data or know something can program computers without having to learn programming.
I agree with that.
I like that.
Yeah.
All right. Well, we are at the end of our broadcast today. Thomas, once again, thanks for joining us so late. I know it's a huge time difference. We have our next episode Wednesday next week at 1 p.m. And we have surprise guests. So can't wait to do more of these episodes with all of you. And thanks for everyone who tuned in for our first show. I hope that you will tune in next time. And Thomas, I hope you'll get a chance to tune in. For those of you who weren't able to join the live stream today or weren't able to get your questions answered, feel free to ask them in chat, and I'll spend some time after this broadcast and go and reply to you individually. Thanks again, Thomas, so much for joining us. And thanks to Suraj and Jessica as well for joining us in our first episode here. And thanks to the whole PyTorch team.
Thanks for having me, and thanks for watching. It has been a huge pleasure to do this with you.
It's been our pleasure. All right. Bye, everybody, and thanks again so much for joining us. Bye.
See you.
Bye, everyone.